Hello students, today we again discuss some basic points related to wave motion and we focus on mechanical progressive waves. So as the waves are progressive and we know the meaning that oscillatory disturbance traveling through the medium without damping are called progressive waves. So all particles are in vibratory motion or oscillatory motion, and oscillatory motion can be expressed in the by the equation like x is equal to a sin omega t. All particles are vibrating and we represent by harmonic function or sine function. We say that in simple words, the vibratory motion is the simple harmonic motion in case of wave also. So we have to derive such equations for the wave, but we have to call that wave as simple harmonic progressive wave. And the equation related to simple harmonic progressive wave can be the equation of simple harmonic progressive wave. We have to derive that equation by considering the equation like x is equal to a sin omega t. For that, we consider the wave which we have studied in the previous lecture, which is formed on a straight string. Suppose here again there is a straight string AB. This B point is or B end is on the rigid support. It is tight here or it is fixed at this point denoted by B, and A is free. Here when end A completes one vibration, here for end A, if there is one vibration, then it completes the phase of twice pi radian and disturbance reaches to the point say E. Then for the point E, just disturbance is reaching, there is no vibration, the phase is 0 radian. Vibrations, number of vibrations are not started there, the phase is 0 radian. We say that phase difference between A and E is twice pi radian. Simple expression we have taken. In other words, we can say that here E lags, particle we say here, particle E lags behind A by phase twice pi radian. Also we have to note one point that between A and E, one wave is formed, therefore path difference between A and E is lambda. Here path difference between A and E is twice pi radian. Oh sorry, it is lambda meter. Similarly, we can take, if the wave continues here, if A completes two vibrations are there, then its phase becomes 4 pi. E completes only one vibration, its phase is twice pi. But wave travels further like this in the direction of propagation. Suppose this direction of propagation is positive x-axis, So always between A and E there is phase difference of twice pi radian. If we consider another particle, say F, phase difference between E and F is also twice pi radian, because here when disturbance reaches to F, its phase is 0 radian. Between E and F, phase difference is again twice pi radian. So we can write it for further particles also. So we consider only here a pair A and E. So this is true for all succeeding particles. E, F, some particles there, G like this. Then all particles lags behind the particle A. So E lags behind A, F lags behind E, like this. So here we have taken only one pair, that if there is phase difference of lambda, path difference is lambda, path difference is lambda, and phase difference is equal to twice pi radian. So lambda corresponds to phase difference of twice pi. So here lambda is measured in meter. We can take one example, that if the phase difference for the two particles which are separated by distance 1 meter, means path difference is 1 meter, then phase difference can be written as twice pi upon lambda into 1. If the particles are separated by distance 2 meters, then phase difference can be written as twice pi upon lambda into 2. If we continue writing here, if the particles are separated by x meters, suppose here we take the particle P, which is at distance x from the source, then for the path difference of x meter, the phase difference is twice pi upon lambda into x. So this point we have to consider, and this phase difference, it is denoted by delta. So for 1 meter it is twice pi upon lambda into 1. For 2 meters it is twice pi upon lambda into 2. But for x meter it is denoted by delta, and it can be equal to twice pi upon lambda into x. So this phase difference we have to consider here when wave propagates from A point to B point, or A to in the forward direction. Here we cannot, we show only the positive x direction. Instead of showing the reduced support, now we show it is the positive x direction. Then we can write such phase differences. But we have to use only this. Now we write the equation for wave. Suppose for A point we write the displacement y is equal to A sin omega t, because the particle is vibrating along the vertical direction. We represent displacement by y. In oscillation chapter we have taken it as x is equal to A sin omega t. Now we have to take here vertical displacement as y. So this is equation number 1. Now for the particle P, which is situated at distance x, here we write the displacement as y is equal to A sin omega t, but the difference is there, phase difference of delta is there, therefore we have to write here minus delta, as P lags behind A. Here as particle P lags behind A by phase delta. It is lagging, therefore we have used here negative sign, and delta we have already obtained. We substitute here, it is A sin omega t minus twice pi upon lambda into x. This is equation number 3. This represents equation of simple harmonic progressive wave. Equation 3 is the equation of simple harmonic progressive wave. We can take it as simple harmonic progressive wave, and now we modify that equation by using our terms related to the wave motion. How can we modify it? We have twice pi upon lambda. Lambda is constant for the given wave motion. It can be a k. It is called as a propagation constant. We write equation 3 by substituting it as y is equal to a sin omega t minus kx. This is equation number 4. Also, modifications are there for this. We take y is equal to, again this equation. Consider equation. Here we must have to write this distance as lambda, and this one is x. Without disturbing it, we consider equation 3. We write it as y is equal to a sin. Here omega t. Omega can be written as twice pi n. We know omega is equal to twice pi n. Also omega is equal to twice pi on t. Also we have relation v is equal to n lambda. All such equations we use here, and we take the forms of SHP wave. So twice pi nt minus twice pi upon lambda into x. So what we get here, y is equal to a sin twice pi can be taken as common, and we can write here nt minus x upon lambda. This is equation number 5. Simple formulation is there. Y is equal to, also we can write a sin twice pi inside the bracket. Here n can be substituted as 1 upon t. N is equal to 1 upon t. We can write here it in this form. So this one is equation number 6. So this is only the adjustment of various terms by using our basic terms and their relations. So also we write here y is equal to a sin twice pi. N can be taken outside the bracket. We write it here. Consider equation 5. Y is equal to a sin twice pi. N can be taken outside the bracket. We write t minus x upon n lambda. So here a sin twice pi n t minus x upon v. Also it can be written as a sin twice pi n vt minus x. Here v can be taken as common. So many forms we can obtain by using this basic relation y is equal to a sin omega t minus twice pi upon lambda into x. So here we have to use this form, equation number 6, for the superposition of waves. But we have derived all these forms because we have to use all these forms in multiple choice questions as well as in numericals. So this is very basic equation that we have to use in this chapter, as it is related to the basic concepts in 11th standard also. We have to use all these forms. Actually, the equation in 11th book is given is simply in the form of v in terms of v and x, but we have to use all these forms. So here we can write such equations, but you can remember only 4, 5, 6, and all these equations you can derive of your own. Therefore, here we have to note all these equations and use to solve the numerical problems. Here we stop. Thank you.